Hey, differential equations fans. In our last lecture, we reviewed the fundamental technique for solving first-order linear differential equations called separation of variables. The good news is a number of first-order linear differential equations can be separated by that technique. The bad news is not all first-order linear differential equations can be solved by that technique. There are some first-order linear differential equations in which the variables cannot be separated. And that brings us to our next topic, the method of transformation of variables. And here's our goal. Given a first-order linear differential equation in which the variables cannot be separated, transform the equation into one in which the variables can be separated by means of a judicious substitution. And by that I mean a change of variable. And we'll look at the classic example of this. Here's the special case, the classic case of a transformation of variables in which a first-order linear differential equation in which the variables can't be separated is transformed into a first-order linear differential equation in which the variables can be separated. And here's the special case. Equations of the form dy dx equal f of y over x are called homogeneous differential equations. These can always be transformed into a differential equation in which the variables can be separated. Given such an equation, where we write it in the form of dy dx equals some function of y over x, given such an equation, the standard substitution is to let v equal y over x. So see the y over x here? This is going to become v. So our standard substitution, given an equation which can fit this form, the standard substitution is v equals y over x, which turns out to be the same thing as y equals vx. Now, making this substitution calls for a corresponding substitution as well, and I'll talk about that in just a second. Here's the bottom line. Given an equation of the form dy dx equals f of y over x, the substitution v equals y over x, or equivalently y equals vx, requires a corresponding substitution for dy dx. The fact of the matter is this. Making this substitution, v equals y over x, we're eliminating y from the equation. And so we have to eliminate dy dx from the equation also. And yet, since we're eliminating y from the equation and replacing it with v, we're going to have to eliminate dy dx from the equation and replace it with its equivalent in terms of dv dx. So here's how we do this. Given y equals vx, we differentiate both sides with respect to x. And the left side is just dy dx. The right side, this is a product, so we're going to use the product rule. First times derivative of the second plus second times derivative of the first. Derivative of the first, that's derivative of v with respect to x. This is the corresponding substitution for dy. So whenever we transform this equation by letting y over x equal v, we're also going to have to replace this expression, dy dx, with v plus x dv dx. Let's look at a few examples. Let's try this one. X squared dy dx equals y squared 2xy with initial condition when x is square root of pi over 2, y is 0. Now, I don't think we can separate the variables, but with the standard transformation of v equals y over x, I think we can turn it into an equation in which the new variables can be separated. And remember my target. I'm trying to get f of yx, rather, dy dx equals f evaluated at y over x. So I'm just going to do this blindly. I'm going to get dy dx by itself. I'm going to divide both sides by x squared and see what happens. I've got my dy dx on the left, and somehow I want to turn this into a function of y over x. And already I can see how this is going to happen. Y squared over x squared, I can write that as y over x, quantity squared. 2xy over x squared, I can write that as 2y over x. Ah, son of a gun, that was easy, 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 easy. Here it is, f evaluated at y over x. This is a function of y over x. And so I'm going to substitute v equals y over x and the corresponding substitution for dy dx what is that? V plus x dv dx for dy dx. I'm going to substitute v for y over x, and I'm going to substitute v plus x dv dx for dy dx. Our equation dy dx equals y over x quantity squared plus 2y over x becomes, let's see, for dy dx we substitute v plus x dv dx, and for y over x we substitute v. So this is the new equation. And I claim that this can be separated. Let's see. I'm going to move this v over to the right. I'm going to subtract v from both sides. So now I have v squared plus v on the right. And I'm going to divide both sides by v squared plus v. Then I'm going to divide both sides by x. And then I'm going to multiply both sides by dx. And dv dx times dx, that's the differential dv. So now we have our variables separated. We have our variables separated, and we can integrate the son of a gun. Let's do that. And oh dear, how do we do this? I can't let v squared plus v equal u and use u substitution. If I let v squared plus v equal u, I'm going to be looking for du up here, namely 2v plus 1, and it ain't here. If I let v squared plus v equal u, I ain't got no du up here. So I can't do this by u substitution. You know what I think? I think we're going to have to use Mr. Partial Fraction Decomposition. So let me clear the board. This is where we're at. And I have to figure out how to integrate this thing. And it seems like partial fraction decomposition is the way to go. Let's see if I can do it. I take my expression, 1 plus v squared, 1 over v squared plus v. I factor the bottom, v plus 1. And then I write it as the sum of two separate fractions. Okay, what do I do now? I solve for C1 and C2 using judicious choices of V. And before I do that, I'm going to have to multiply both sides by the denominator. And if I'd been thinking ahead of time, I would have written this denominator in factored form. Oh well. There's always the next step. Oh, and we have a lot of good canceling going on. Okay, I like this. And I'm going to solve for the unknown constants C1 and C2 by substituting in judicious choices of V. I'm going to pick values of V that will make either this term disappear or this term disappear. So I'm going to choose some judicious choices of V to make either this term disappear, in which case I can solve for C2, or I'll make this term disappear and I can solve for C1. Now, let me ask you something. What would V have to equal to make this term right here disappear? V equal -1, right? Okay, let's try it. When V is equal to -1, we have 1 on the left side, 0, plus C2 times V, where V is -1. So C2 is -1. Well, that was easy. Let's do it again. What choice of V could I make to let this term disappear? Or what choice of V could I make so that this term disappears? V equals 0, right? So I'll let V equal 0. And on the right-hand side, I have 1. And on the left-hand side, I have 0 plus 1 is 1. So that's C1 times 1 plus 0. And that gives me C1 equals 1. And let me just make sure that it works. If I multiply top and bottom here by V plus 1, I have -V plus 1 up top. If I multiply top and bottom by V up here, I have V. Let's see, is that going to work out right? Uh-oh, I don't like that. Oh, C1 equals 1, I beg your pardon. And C2 equals -1. Okay. Good thing I checked, huh? Okay. Since I messed up just a minute ago, let's make sure I got it right now. Multiply top and bottom here by V plus 1. Multiply top and bottom here by V. And I have V plus 1 minus V is 1. 1 over this garbage. Yep, that's what I need. Okay, this is right. Okay. This is what our expression becomes, and we can integrate both of these things. One over V dV, that's natural log absolute value of V. 1 over V plus 1 dV. Well, this fits the form of 1 over U du. If V is U, then dV is du. So what we're going to get is natural log of V plus 1. Voila. Now let's think about our initial condition. Yx, what was it? Xy rather. Xy equals square root of pi over 2. 0. Oops, I don't have any x's and y's yet. Okay. Well, what was v? Wasn't that y over x? I'm going to combine these terms. The difference of natural logs. Don't we have some sort of a formula for that? Let's see. Natural log of A over B equals natural log of A minus natural log of B. Well, you know, this is an equation. And even though we're English speaking and we read English from left to right, equations can also be read from right to left. So here's what I'm going to get. I'm going to get the quotient of these two things. And let's see, what does that become? Natural log, absolute value of y over y plus x is equal to the natural log of x plus c. Okay. Ew, I don't like that. I think I'm going to raise both sides to the power of e. How about that? Get rid of the natural logs. And the left-hand side becomes y over y plus x. And the right-hand side becomes e to the natural log of x times e to the c. And e to the c is just a constant.